Today, we are taking a 10-minute walk along a perfect grid, taking words with numbers injected into them and sorting them into correct order, and then we are playing around with Fibonacci numbers. Hello world, and this is versus Codewars. We begin today with the warm-up segment, a series of easier katas in order to prepare for the more difficult katas later in the episode, starting with a function that takes a number and returns its negative counterpart, if it is not already negative. Let's go ahead and hit train on this one. Our function signature is const to make negative, and it takes a number as a parameter. What we'll go ahead and do is, if number is less than or equal to 0, we just go ahead and return the number proper. Otherwise, we'll use the minus sign unary operator to make the number negative. Alright, let's go ahead and punch this into Codewars here and see what that looks like. Let's hit attempt. And we are good on that one. Our next warm-up is the sum of two lowest positive integers. This function, given an array of numbers, returns the sum of that array's two smallest elements. Alright. Each array will have a minimum of 4 positive integers. No floats and non-positive integers will be passed in. Let's go ahead and give this a try here. Alright, our function signature is const sum two smallest numbers, and it takes an array of numbers. What we'll go ahead and do with this one is numbers dot sort. Alright, if you use the array object sort method with no predicate function, it will by default sort the array's values in ascending order. Alright. What we'll do from here, we'll take the resulting sorted array and we'll run the slice method from 0 to, I think, 2. And then we'll take that resulting array there and run that through reduce. Passing in our accumulator and our number. Alright, let's go ahead and run that. Let's go ahead and run a sample through here first. Let's go ahead and take this array here from the Kata instructions here. We're going to run that through console.log, sum two smallest numbers, and we're going to pass in that array right here. Alright, let's run that through node and see what that looks like here. Node, warm up sum of lowest. And that is probably not what we were expecting here. I expected to see 7 out of there.
Okay.
Alright, first let's go ahead and console.log that array and see what that looks like.
Sorted. So I'm going to note again. Alright. Maybe we do need a predicate function in here. Maybe we do need to explicitly,
Maybe we do need to provide a predicate function here and explicitly sort this in ascending order. Yep. I think that's the problem here. Let's go ahead and punch this into Codewars and see what this looks like here. And we are good on that one. Our next warm-up kata, we are calculating the growth of a population in a small town where the population P0 is set to 1,000 at the beginning of a year. The population regularly increases by 2%. That is 1,000 times 0.02 per year, and more over 50 new inhabitants per year come to live in the town. How many years does the town need to see its population greater than or equal to 1,200 inhabitants, for example? Alright, let's go ahead and give this one a try here. Our function signature is NB year, and it takes 4 parameters. P0, the town's initial population, percent, the percentage by which that population grows each year. AUG, what does that stand for? AUG, inhabitants coming or leaving each year. And P, which is the population that we want to surpass. Alright, well, we'll go ahead and try here. Let's start with our current population, which we set to P0. And while current is less than P, our goal population, what we'll go ahead and do is current plus equals, in our parentheses, current times percent plus AUG, the number of people coming or going. We'll set a counter here that keeps track of the number of years that elapses in order for this population to reach the goal. And we'll go ahead and increment that in our while loop here. And that is what's going to be returned in this Kata solution. Alright, let's go ahead and do a little testing here. Console.log NB year. Pass in 1,000. 0.02. I imagine this is like the decimal form of the percentage that was mentioned before. We pass in 50 and then 1,200. I expect to see 3 return from here. Let's punch this in a node and see what that looks like here. Warm up, population growth. Whoops, not nodes. Node. And we do see, in fact, 3. Let's go ahead and punch this into Codewars and see what that looks like here. And run the tests. And we have a problem. Expected one to equal 15. Alright, let's go ahead and console.log our inputs here. P0, percent, AUG, and P. Oh, okay. It looks like this actually needs to be the actual percentage. Let's go ahead and run this through the other tests here to confirm my suspicion. 2.08, 1.0. Ah, okay. Alright, what we'll go ahead and do with that in mind.
You have percent divided by 2% divided by...
Alright, let me see the Kata instructions here.
.02, okay. Remember, percent is 2. 2 divided by 100 is .02. Alright, let me run some console logs here. Current years. You want us to note here.
Let me change this solution up a little bit here.
While true, plus plus, if current is greater than or equal to P, break. And move this years plus plus down below that if statement here. Yeah, I might want to map that format too. Might need to rethink that.
Alright, let me go ahead and redo this here. Something doesn't seem right with this. Alright, we're keeping track of our current population. Keeping track of the number of years elapsed. While current is less than our goal population. We take current and we add to that the floor of current times percent divided by 100. And then we add in the number of people coming and going. If current is greater than or equal to our goal population, after that we break out of the loop. Otherwise, we increment our years. Try that through node. And we do need to return our years. We do receive our 3. Let's try punching this into Codewars and see what that looks like. Run the tests. Still problems. Expected 14 to equal 15. Maybe get rid of this if statement here. Reflect that in the Kata. Oops. Run a test. That test passes. Let's attempt this solution here, and we are good on that. Our last warm-up kata is called 2 to 1. Given 2 strings, S1 and S2, including only letters from lowercase a to lowercase z. The goal of this kata is to return a new sorted string, the longest possible, containing only distinct letters, each taken only once coming from both strings. Let's go ahead and give this one a go here. Const longest. str1, str2. Take our 2 strings as parameters here. What I think we'll go ahead and try here is const char set equals new set. We'll take our str1, str2. str1 plus str2, concatenate them together, split them into their individual characters, and then we pass that resulting array into a new set, which ensures that only distinct characters will be in this set. Our goal here is to return the set sorted. But first, let's go ahead and console.log that set and see what that looks like. Char set. We'll spread that out into an array here. And we'll go ahead and grab these strings from our sample here in the kata instructions. We're going to run that through node and see what that looks like here. Warm up 2 to 1. And we should have an array with only unique characters from both of our strings. What we need to do now is sort them in, I think, ascending order. Let's just try using the sort function here first. And that does seem to work. So what we'll go ahead and do, we're going to go ahead and return, spread that set out into an array. And then we'll run that array through sort and return the resulting array. Let's go ahead and console.log that and see what that looks like. And we do have our array sorted. Let's go ahead and punch this into Codewars and see what that looks like. Run the tests. We have a problem, because we need to join the string back together here. Let's try that again. Still problems. Because we need to do that in the Kata solution as well. Let's try that again. And we are good. And that concludes this morning's warm-up segment. Let's go on to the next kata. Welcome to the city of Cartesia, a city where all roads and blocks are laid out in a perfect grid. You live in the city and you arrived 10 minutes too early to a doctor's appointment, and you decide to pass the time by going for a walk. The city of Cartesia provides you with an app that you can use on your phone for generating a route for your walk. That route is represented by an array consisting of any combination of the lowercase letters N, S, W, and E, each one corresponding to the directions north, south, west, and east, respectively. For each letter, you walk a single block, and it takes exactly 1 minute to walk that single block. Given an array with the aforementioned parameters, the goal of this kata is to determine if it takes exactly 10 minutes to walk that generated route, and if that route takes you back to your starting location just in time for your appointment. Let's go ahead and get started with this one. Alright, we have this one parameter here, walk, which is our array. What we'll go ahead and try is const endpoint. And what we'll go ahead and try here is walk.reduce. Pass in our accumulator and our direction. And for an initial accumulator, we'll have an object consisting of X and Y. So what we're doing here, obviously we have our start point here, 0, 0, which is the location of our doctor's office. We want to take this array of directions and run that through the reduce method. In our predicate function, we have our accumulator, which will be our start point here to begin with, and our current direction character. And what we'll go ahead and do with that is if, or rather switch direction. And in the off event that an uppercase letter is provided, we'll do direction.toLowercase. And what we'll do is, if the direction is W or west, we'll return our accumulators, a spread of our accumulator, and then do X minus 1. If it's east, represented by a lowercase e, we'll do just that, only increment X instead of decrement it. Now, if it's a lowercase n, representing north, we'll do spread out our accumulator and set Y to Y plus 1. And for the lowercase s, representing south, we'll spread out our accumulator here, and then decrement Y. And in the default case, just return our accumulator. So what we're doing here, we're taking the direction character, we're changing it to lowercase in the off event that we're given an uppercase letter, which won't be the case for this kata, but it's always a good idea to check. Alright, we'll check to see if, we'll modify this object here depending on the value of this direction here. And we do that by using the object spread logic to spread out our accumulator object here, and then modify the appropriate direction here, either incrementing it or decrementing it based on the direction we're given here. If it's W or west, we take X and decrement it. If it's E for east, we take X and increment it. If it's N for north, we take Y and increment it. And if it's S for south, we take Y and decrement it. And we modify our accumulator object as appropriate. Now what we need to do, we need to return true if endpoint.x is 0 and endpoint.y is equal to 0. If that's the case, that means we are back at our starting location and we can return true from this walk. We do need to do one more thing though. We need to check the length of our walk array here. If walk.length is not equal to 10, then we know that this walk is not going to take 10 minutes for us to complete. And this Kata wants a route that'll bring us back to our starting point in exactly 10 minutes. So in that case, we just return false up here. And don't bother with the reduce call here. Alright, let's go ahead and test our Kata function out here. Maybe with this array here. And I expect this to return false. Console.log is a valid walk. Pass in our directions here. Let's run that through Node and see what that looks like here. And we do in fact see false. Let's try another test case here. This array right here. Run that through Node here. Y is not defined.
Why is Y not defined here? Line 33. Okay, we'll go ahead and get this here. Reduce our accumulator. We have this additional accumulator right here. Let's go ahead and console.log that.
Ah, there we go. There we go. And we do, in fact, see true. Alright, let's go ahead and run this to Codewars and see what that looks like here. Run the tests. And we are good. When using a JavaScript object as the default accumulator in the arrayObjects reduce method, remember that the predicate function in the reduce method does not have access to that accumulator object in its this context, as far as I'm aware for arrow functions. If it's anything different for the regular function syntax, please let me know. You'll need to explicitly access the accumulator object before accessing its properties instead. Given a string, with each word in that string containing a numeric character between 1 and 9, the goal of this kata is to sort those words in the order denoted by the number in each of those words. Let's go ahead and give this a try here. First, I want to see one thing. The kata says that each word will have a numeric character between 1 and 9, but will there be more than 9 words? I want to see that first. So what I'm going to go ahead and do is console.log words.split with a space and then get their length. Whoops. When I log their length, I'm just going to go ahead and run that through each of the tests here. Alright. That being said, let's go ahead and get started with this one here. What I think we'll go ahead and do is we're going to go ahead and split the words, the string, into its individual words with the space separator. We're going to take that resulting array and run the sort method on it. And we're going to pass in a predicate function to that. We're going to work on that just shortly. We're going to take that resulting array and join that back together with a blank space. Alright, let's go to work on this sort predicate function here. What I think we'll go ahead and do alright. Trying to find a numeric character in it here. I think we use a regular expression for that. Let's try that. It's to numeric equal, yeah, const a numeric equals a dot match. Alright, we'll go ahead and set up a little regular expression up here. Const numeric regex. Zero through, well, actually 1 through 9. I'll run that through our new string.match here. We'll do the same with the second string here in our sort function. Let's go ahead and console.log those and see what that looks like. Console.log a numeric b numeric. Right, let's go ahead and take one of these sample strings here and put that in our local solution here. Console.log order. Pass that in here. Let's run this through Node and see what this looks like. All right. Four. All right, what I think we can do from here is parse int a numeric minus parse int b numeric. Let's try that. Yeah, I think that works just fine. Let's go ahead and try another test case here. Let's do a little bit of a string of my own. Let's try a little bit of a string of my own here. Yeah, I think that works. Let's go ahead and punch this into Codewars and see what that looks like. Run the tests. And we are good. Not really much to say about this one, except instead of looking for the numbers 1 through 9 in our regular expression, I could have just used the \d character class to look for numbers in general. I could also have saved the calls to parse int and our sort method's predicate function, comparing the two characters instead of converting them into numbers in order to achieve the same result. Before we go on to the next kata here, we need to have a discussion about the Fibonacci sequence, which is a series of numbers such that the next number of the sequence is found by adding up the two numbers before it. For example here, we have this 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on. Alright, to get this 5 here, we would need to find out the two elements of the sequence before it, which is 3 and 2, and add them together. We're going to go ahead and try implementing this here before we go on to our next kata here. What we'll go ahead and try here is, if index is less than 0, less than or equal to 0, return 0. If index is equal to 1, we'll return 1. Otherwise, what we'll go ahead and do, we're going to do a little bit of recursion here. And we'll do this. Return Fibonacci at index -1 plus Fibonacci at index -2. Alright, let's go ahead and test this out here. Console.log Fibonacci, and we'll pass in. We're going to try to get to the 1, 2, 3, 4, 5, 6th element of our sequence here. And I expect to see 5 here. Let's go ahead and punch this into node and see what that looks like. Node, intermission, Fibonacci, and we get 8 instead. Base 0. 0, 1, 2, 3, 4. Yeah, okay. Yeah, does that need to be... I wonder if that needs to be base 1. Or if we're dealing with a base 1 sequence. So at the 5th element of our sequence, assuming the sequence is base 0, we should get our 5 here. Let's try the 6th element of our sequence here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's try the 10th element of our sequence here, and we do get our 34. And that is basically how the Fibonacci sequence works. With that in mind, let's go ahead and do our next kata. Given a sequence of 3 starting terms and an index, the goal of this kata is to generate a Tribonacci sequence of numbers, in which the next number of the sequence is the sum of the 3 previous elements of the sequence instead of 2. And we generate this sequence up to the given index here. Let's go ahead and give this one a try, shall we? Alright. First and foremost, if our index is less than or equal to 3, we just go ahead and return that signature sliced to index. Now let's go ahead and test that out here. Console.log Tribonacci 1. I think we pass in our 3 here. Let's run that through node and see what that looks like. Node Tribonacci, and we do have our 1, 1, and 1. Now, according to the kata instructions, our signature, as they call this initial array, will never contain more or less than 3 elements. Alright, with that being said, for let I equals 3, I think. Alright, first we'll go ahead and do something like this. While signature.length is less than index. And we'll do signature I think we'll do signature dot push we'll push in the values of signature dot at signature dot length -1. Whoops. 3, 2. And we'll go ahead and return that signature down here. Alright, let's go ahead and punch that in a node and see what that looks like here. What we'll go ahead and do, we'll grab one of these tests here. Yeah, just punch in 10 here. Let's punch this in a node and see what that looks like here. 1, 1, 1, 3, 5, 9, 17, 31, 57, 105. Alright, that is what we want to see here. Let's try another one of these test cases. Zero, 0, 1, 1, 2, 4, 7, 13, 24, 44. That is what we want to see as well. Let's do a big one here. Back our initial sequence here. Let's try 1,000 elements here. Doesn't really take that long at all to generate that kind of a sequence here. And liking what I'm seeing here. Alright, before we punch this into Codewars, let me explain what's going on here. We have our Tribonacci function, and it takes 2 arguments. The signature, which is an array of the 3 starting terms that we want to use to start our sequence, and the index. This index is how many terms should be in the generated Tribonacci sequence. We check to see if this index given is less than or equal to 3, in which case we just go ahead and return a slice of the initial signature up to that index. Otherwise, we go into a while loop here that continues as long as the length of this signature is less than the index that we passed in. And what we do is we push in a new element into our signature that is equal to the sum of the element the last inserted element of our signature, the second last inserted element of our signature, and then the third last inserted element of our signature, indicated by the signature at index signature length -1, then -2, and then -3. We continue this until the length of the signature is equal to the index that we pass in, and then we return the signature down here. Let's go ahead and punch this into Codewars and see what that looks like. Alright, we'll run our tests and try submitting. And we are good. Here you saw 2 different implementations of the Fibonacci and Tribonacci sequences. The Fibonacci implementation, which you saw in the intermission before this kata, uses recursion to get the last 2 elements of the sequence to add them together to calculate the next element of the sequence. The Tribonacci implementation, which you saw in this kata solution, uses a while loop and the array object's push method. Now, in this while loop, which continues as long as the length of the signature array that was passed into the Kata solution does not equal or exceed the index, it takes the last 3 elements of the Tribonacci sequence, adds them together, and then pushes the sum into the signature array. That sum is the next element of the Tribonacci sequence. One thing I could have done better here, though, was to use the array object's slice method, passing in a negative number, which begins slicing relative to the end of the array rather than the beginning of the array. I would have taken the resulting array and run that through the reduce method, adding those elements together to get the next element of the Tribonacci sequence. Sticking with the theme of Fibonacci sequences, given a number, the goal of this kata searches for 2 consecutive terms in the Fibonacci sequence, such that the product of those terms is equal to the number passed in. Alright, the return value of this function is an array, a 3-element tuple containing the 2 consecutive elements of the sequence, and either true or false. True if the product of those terms is equal to the number passed in, or false if the product of those 2 numbers is not, more than likely greater. Let's go ahead and give this a try here. Alright. For this one, we're probably going to need the while loop, a variant of the Fibonacci implementation. So what we'll go ahead and do is, I think we'll try this. Const sequence equals 0, 0. Alright, I still have this tab open on the Fibonacci sequence here. So yeah, 0, 1. And we'll just do a little bit of an edge case here. If product is equal to 0, then we'll just go ahead and return up here 0, 1, true. Alright, and we'll go ahead and do a while loop, I think. Don't mind the phone. Anyway. We'll do sequence dot push sequence at sequence dot length minus 1 plus sequence at sequence dot length minus 2. And then what we'll go ahead and do, we're actually going to go ahead and return we actually need to go ahead and calculate this next element up here. Constant next element. We'll take these. And then we'll push that into our sequence here. Alright, what we'll go ahead and do from here is we're going to multiply this next element and the last element of our sequence here. We're going to go ahead and do this. Current product. We'll take that. Next element times sequence at sequence dot length minus 1. And then if current product is equal to the product that we passed into this Kata function here, we'll go ahead and return I think we'll go ahead and do this push at the end of our while loop here. Sequence at sequence length -1. Next product true. Or I have a better idea. If current product is greater than or equal to product, then we'll have this tuple here with the last element of our sequence. The next element of our sequence here, what would have been the next element of our sequence here. And then either true or false, depending upon whether current product is equal to product. All right, so what we're going ahead and doing here is, first we check to see if the product passed in is a 0, in which case we just return 0, 1, which is the first two elements of the Fibonacci sequence, and true. All right, we then go ahead and generate the first two element, an array. We go ahead and create an array with the first two elements of our Fibonacci sequence as seen here. And then in this while loop here, we calculate the next element of the sequence by taking the last two elements of our sequence and adding them together. All right, then we multiply together this next element here and the last element of our sequence, and we put it in current product right here. We then check to see if current product is greater than or equal to the product that we passed into this Kata function up here. If it is, we then return a tuple with the last element that we put in our sequence array right here, this next element, what would have been the next element of our sequence here, and then a Boolean flag for the third element of the tuple here, which is set to true if current product is equal to the product that we passed in, or false if it's not, and more likely greater than the product that we passed in. If we make it past this if statement here without returning here, we just go ahead and push this next element into our sequence and we continue the while loop. Alright, let's go ahead and test this out here. We got some tests down here. First one, we're going to go ahead and do console.log product fib. Let's pass in something from one of the examples here. Let's try 714. Alright, let's feed this into Node and see what that looks like here. And we get 21, 34, and true. Let's try passing in 800. We get 34, 55, and false. That is sound with these examples here. Let's try some of these tests here next. And we got a large looking number here. If we punch in 4895, we expect to see 55, 89, and true. 4895. And we do in fact see 55, 89, and true. What about 5895? 89, 144, and false. That's good. And now let's try some larger numbers in our sequence here. How about this? I think that is 74,049,690. That's a sizably large number, is it not? And we get 67, 65, and 10, 9, 46, and true. We love to see it. Let's try a bigger number. I think that is 193,864,606. Executes that pretty quickly and correctly too. Let's try another large number. This is 84,049,690. And we do get the desired result here as well. I like what we are seeing here. Let's go ahead and punch this into Codewars and see what this looks like. Run the tests. And we are good. Here is the better code solution of the day. Pay mind to the code snippet you see below me here. What you see here is the creation of an array of two elements, 0 and 1, and then the use of what's called a destructuring assignment to assign the two elements of that array into distinct variables, in this case A and B. You see this destructuring assignment again in this while loop here, where A and B are assigned to the values of B and A plus B respectively. I knew this was legal in Python, but I didn't know until just now that this was also legal in JavaScript. You see in the end the return of the tuple again, where you have A, B, and then either true or false depending on whether A times B is equal to the product passed in or not. And that's going to do it for today's episode of Versus Codewars. If you liked the video or you learned something new, drop a like and subscribe to this channel to see me take on more coding challenges on Codewars. As always, if you think there's anything I can do to improve on my code, feel free to drop a suggestion in the comments section below. I hope you have a wonderful day, and I will see you on the next episode of Versus Codewars.